Hello, very good morning students. So welcome again in this video lecture series for ACD. Let's take a review of last lecture what we had. So we had this Miller theorem, is it? Now before starting with Miller theorem, I told you that we are about to start with high frequency response, is it? Here it is. We supposed to start with high frequency response, and to start with high frequency response we need two important things that we are going to use in high frequency response. What are those? First one is Miller theorem and second one is the square wave testing, is it? So Miller theorem we have finished with, and now we are going to start with square wave testing. Let's see. Now those Miller theorem and square wave testing, those are some concept that I'm going to use or I'm going to apply at high frequency analysis, is it? So that's why we are studying those things before high frequency analysis. So now Miller theorem as we are done with, so let us start with square wave testing, is it? Let me write it here. Square wave testing. Now what is that square wave testing? Basically it is actually a square wave testing of an amplifier, is it? So if you have an amplifier, is it, for example, if I give you one amplifier circuit and if I ask you tell me whether this amplifier is working fine or not, that's what it is. See, simple question. I'm giving you one amplifier circuit and I'm asking you tell me whether this amplifier is okay, whether this amplifier is practically accepted. Say, tell me yes or no. Now if you want to tell me the answer, then somewhere you have to test it. You have to check whether this amplifier is okay or not. So how you will check then? There is one traditional method. Yes, to check amplifier we need to check its frequency response. If amplifier's frequency response is something like this, then amplifier is okay, is it? Or if your amplifier is too good, then it will give ideal frequency response. That case never possible. But still I'm saying this is what ideal and this is what practical frequency response. If amplifier is giving frequency response in a range of some frequencies, that is a frequency bounded response, then obviously you will say amplifier is okay. But to get frequency response, what you will need? You need to apply some input voltage. Look at this, you have to apply some input voltage. You have to measure output voltage for every frequency. Look at this, this is what your observation table. For every frequency you will measure output voltage. Then you will take 1, 2, 3, 4, like you will take more than 100 readings, is it? For every frequency you will measure output voltage and then you will calculate gain. Then you can calculate gain in dB and then you will plot a frequency response of gain which is in dB versus frequency. Then you will calculate it lower cutoff frequency, then higher cutoff frequency. That's what bandwidth you will get. And then if that lower cutoff frequency and higher cutoff frequency and bandwidth, if it is matching with your desired thing, your desired bandwidth, your desired frequency range, then you will say that amplifier is okay, is that? So it means to answer the question whether the amplifier is okay or not, whether the amplifier is practically accepted or not, you have to follow a procedure. You have to test the amplifier by the long process of frequency response. Look at this. So taking frequency response is the traditional method, traditional option, is it? But apart from the frequency response, we have a nice shortcut. What is the shortcut? The shortcut is, say if I give you amplifier, what you do? You apply a square wave as an input to the amplifier. You apply square wave and then check the output shape, check the shape of the output. See, the conclusion the conclusion includes this: if this square wave that you have applied as an input, if this square wave you are getting at the output as it is, see output is exactly same as input, then your amplifier is actually it's too good, is it? Or what I can say, it is ideal amplifier, practically accepted, even though that thing does not exist, that ideal amplifier. But still we are saying if you are getting exact output same as input, that is identical input and output waveforms, then you will say amplifier is good. If at lower frequencies, see, for every frequency you supposed to get square wave as it is. If at lower frequencies means what? You apply input signal, make a frequency very low, is it, or change the frequency to a very low value, then you will get some decrement in the output voltage. Look at this, some decrement in the output voltage, is it? Then what you will conclude? You will conclude that there is a problem at lower frequencies, is it? See, without taking its frequency response of an amplifier, I am concluding that there is a problem at the lower frequencies. There is a problem with the gain of an amplifier at lower frequencies. Is it? Why? Because I am getting that much tilt. Is it? That much tilt I am getting, that much decrement in the output voltage I am getting. Is it? So what is that tilt? What is that decrement? That we will discuss further. But for the time being, apply square wave, make its frequency very low, and if at lower frequencies you are getting some reduction in the output voltage, then conclude that there is a problem with the lower cutoff frequency. There are some issues, or at lower frequencies I am not getting the perfect gain. That's what the conclusion, is it? So it is not a problem actually, is it? There are reasons why there is a decrement, is it? There are reasons. We can't say it is a problem. It is a behavior of an amplifier. It is not problematical condition actually, is it? Now leave it and then apply the same signal with higher frequencies. Then at higher frequencies you will get this. Is it? Okay, let me draw the perfect one. Okay, at higher frequencies you will get that kind of waveform, a sawtooth type of waveform. If you are getting this waveform, it means you have to conclude that at higher frequencies gain is not sufficient, or maybe there is a problem for the frequency response at higher frequencies. That's what the conclusion, is it? Now why I am getting that kind of shape and what conclusions I can draw from that kind of shape, that we will discuss afterwards. But here I can test the amplifier immediately. Right? Those are some immediate conclusions without taking any frequency response. Apply a square wave. If you are getting exact square wave as it is at all the frequencies, your amplifier is good, too good actually. At lower frequencies, if you are getting a sag or tilt or decrement in the output voltage, it means at lower frequencies we are getting reduction in gain. Right? And those things are practical things. Those things are practical things. So that's why I said it's not a problem, it's a behavior. And why amplifier behaves like that, that we will discuss afterwards, is it? Actually we had discussion about that. At higher frequencies I am getting sawtooth waveform. It means at higher frequencies maybe I am not getting sufficient gain. So those are immediate conclusions by the square wave. So that's why it is called square wave testing, is it? Now one by one we will analyze what happens at lower frequencies, what happens at higher frequencies. Actually why it happens, that already we have studied. At lower frequencies gain reduces, is it? Gain reduces, it means output voltage reduces, and that's why gain reduces. Why output voltage reduces? Because of this bypass capacitor, that is CE, and coupling capacitor CC. Maybe it is C in or C out. So those are responsible to decrease the output voltage at lower frequencies, that we have studied, is it? So at lower frequencies output voltage decreases, that much decrement is there. At higher frequencies output voltage decreases, and even the shape of the waveform also changes, is it? Why? Because of stray capacitance and internal capacitances of a transistor. Because of them output voltage decreases. That also we have concluded, is it? But we have not analyzed why gain changes or why output voltage changes at the higher frequency, is it? To understand that, we are studying those Miller's theorem and what is the square wave testing and all, is it? So I think that much about square wave testing is okay. Yeah, apply square wave. If as it is, then amplifier is good. At lower frequencies, if it is a reduction in gain, there is a problem at lower frequency. At higher frequency, shape changes, it becomes a sawtooth. Then there is a problem with the higher frequency. So that's why it means amplifier is practically tested. So it is called square wave testing. Is that? Now, as we started with the square wave testing, let us start with actually square wave. Is it? So this is something that we had in a last lecture. I explained the same thing to my students. It was a revision class actually. Right. So that's what the stuff we need to delete. Let me delete everything and let me write the fresh thing for you people. Is it? So we will start everything. So let me check. Oh, we had a lot of stuff covered in the last session about that sag and tilt square wave testing. Is it? So that's why let me delete it, rub this, and let us start with the fresh thing. We had this. Only figures will keep as it is because those I can use as a reference. So look at this. So now I have an amplifier. Look at this. This is what my amplifier. I'm just drawing a box of an amplifier. This is input signal. This I'm talking about. And here this kind of output voltage I'm getting. So instead of square wave, I'm considering a part of square wave, some part of square wave, or what I can say a pulse from the square wave. Square wave is actually what? A square wave is a shape like this continuous chain. Is it? Out of this continuous chain, I'm just considering that much part. This is what. Is it? And obviously it's a periodic signal. So same cycle will repeat after a pulse period. Is it? So here T1 is the pulse width or the period or positive period, whatever you say. So pulse width, in my language I'm saying pulse width. So T1 is the pulse width, V is the input voltage magnitude, or what I can say input voltage amplitude. So if this input signal I have applied to my amplifier with a low frequency, then I will get that kind of output voltage. Now look at this. Output voltage is this is the output voltage. Look at this. Output voltage is not having the same shape as the input voltage. Why? Output voltage is slightly tilted. Is it? Slightly reduced. Is it? That reduction in output voltage is called sag. That reduction is referred as a sag, or there is alternate name tilt. Is it? So reduction, sag or tilt in the output voltage at lower frequencies. It happens. So look at this output voltage. What is the desired output voltage? Output voltage desired level is V. Is it? If I am saying a unit gain of this amplifier, then output desired voltage is V, because amplifier gain is unit 1. So input voltage will be same as output voltage. So desired voltage is V, but actually I am getting how much? V1. So the difference, that is V minus V1 with respect to total V, is called sag, or let me write equation as sag is equals to V minus V1 divided by V. Is it? So V minus V1 divided by V, this is called sag, or there is an alternate name tilt. Or if you want percentage sag, then clearly you can write V minus V1 divided by V, just multiply it by 100 and you will get the things done. Is that? So if output voltage reduces at lower frequencies, then tilt or sag is there. That reduction is basically called as a sag. Is it? Now see, I'm saying at lower frequencies sag is produced. Is it? But at lower cutoff frequency, how much sag is produced. That's what I'm interested in, because at my frequency response, look at this. If I'm saying it is a frequency response, then let me draw the frequency response. It's not working now as so at lower frequencies. Look at this, at lower frequencies, this is what actually frequency response. So here it is 3 dB frequency. This is 3 dB frequency. We call this as lower cutoff frequency. So gain decreases, output voltage decreases, and output voltage decrement is tolerable up to minus 3 dB. Is it? At this level, I am getting my lower cutoff frequency. At minus 3 dB means it is 1 divided by root 2. That is what 0.707, the magical level. Is that? So output voltage reduction is tolerable up to 0.707. That is my lower cutoff frequency. Is that? So at lower cutoff frequency, how much sag is produced, or I can relate this lower cutoff frequency with sag. That's what we have to find. I will find the relation between lower cutoff frequency and sag, because the tolerance level is 0.707, that is minus 3 dB. So up to minus 3 dB or at lower cutoff frequency, how much sag is there? Is it? That's what I will find. I will relate lower cutoff frequency with the sag. So let us start with, so what is that sag? Basically it is V minus V1 divided by total V. Let me write it here. Sag is equals to, what is T1? T1 is a pulse width. Understood? So can I copy that thing? Let me check if I can copy this, that much part. Yes, it's copying now. Okay, it will take some time, and then I'll paste it here. This is what my actual sag is, V minus V1 divided by V. Now look at this, output voltage is decreasing between the time period of T1, that is in the time frame of T1, that is pulse width. Is it? Look at this, the decrement I have said it is X, the total desired output voltage I am saying it as Y. So X is how much percent of Y is what sag is. Agreed? So sag thing is cleared. Now I need to relate it with the lower cutoff frequency. Right? Now look at this. You have studied Thevenin's theorem. So what Thevenin's theorem does actually? Thevenin's theorem. Any circuit, look at this, any circuit is converted into one voltage source and one resistor, RTH and VTH. You have studied Thevenin's theorem, so you know that. Any circuit, any electronic circuit, or what I can say in simple language, any network, because you have studied in network analysis. So any network is converted into one voltage source in series with one resistor. Why we are doing this, or why Thevenin's started this? Because it will become easy to analyze the full network. Is it? Whatever resistors are present, we will calculate equivalent resistance. Whatever voltage source and current source are present, we calculate its equivalent voltage source and convert the whole network into one resistor and one voltage source. Like this, if you are studying amplifier, that amplifier can be converted into simple RC pair, that is one resistor and one capacitor. Every amplifier. How I can convert that into RC pair, that you will study in higher frequency response. Is it? So when we start with higher frequency response, you will come to know that all the amplifier circuit can be converted into RC network. Is it? So that thing you will definitely study in the next lecture or next to next lecture. Is it? But whatever we are going to study, I am using some part of that here in this analysis, because this things will become easy then. Is it? Why? Because see, now it means if I'm saying this is the output of an amplifier, it means what I can say, this is output of an RC network, because amplifier eventually is converted into RC network. Like a Thevenin's theorem, every network is converted into voltage source and resistor. Like this, amplifier is converted into RC network. So now for this RC network, look at this, for this RC network, output voltage changes from V to V1 within a time period of T1. Is it? Do you understand that? In time T1, voltage V reduces to V1. Is it? That is rate of the reduction. See, output voltage is actually V, it is reducing towards V1 during time T1. Now, if I increase T1, this is output voltage reduces towards V1 during the time T1. Now, if I increase T1, or if I say if T1 tends towards this RC, RC is a time constant. Look at this, it is a RC circuit, that is RC time constant. If T1 tends to RC, is it, then this V1 start going towards value of 0. जितना time बढ़ेगा, ये जो V1 है, look at this V1, initially it was that, then again time increases, it goes down, it goes down, it goes down, it goes down, it will go to 0, that is V1 will go to 0 if time T1, that pulse width tends to RC time constant. So that is what actually, what I can say is a rate of change, is it? So when, what I will say when RC is very less than T, T is the time period of applied signal actually. So if you don't understand that, then let me rub this, because see, I don't want to enter into new part. So whatever theory we have, will go with this. So that is what rate of change. So this is what rate of change. Now this V minus V1, is it, that is what reduction. Yes, V minus V1 is the decrement in the output voltage. Look at this, that much is the reduction, is it, V minus V1. So that reduction occurs within a time of T1. Look at this, where T1 is the what, pulse width. T1 is pulse, T1 is a pulse width. Now output voltage decreases linearly for the period of T1. It means now what, or how can I represent that in equation? Okay, let me write output voltage. What is the output voltage? Output voltage decreases. Output voltage decreases linearly for period of T1. For period of T1, output voltage decreases linearly for the period of T1, because T1 is the pulse width, is it? So we can write, now see what I'm writing, it is V minus V1 divided by V is equals to T1 divided by RC, is it? It is T1 divided by RC. Now let me check. Let me keep it here. Now this V minus V1, what is that? It is a reduction. I will write, it is reduction to the actual voltage, reduction, and this is what, actual voltage, or we can say desired one. Desired output voltage, isn't it? When the reduction occurs, when T1 tends to RC. So that's why I'm clearly writing V minus V1 divided by V, that is equals to T1 divided by RC. When T1 tends to RC time constant, then that sag comes, or tilt comes, is it? Or in another language, is it, the same thing I will repeat, but now the language will be different or the sentences will be different. Now what are my sentences now? Look at this, the reduction that is V minus V1, that might create in output voltage, is it, in the time t1, is it, ये रिडक्शन हो रहा है कितने टाइम में हो रहा है, t1, इतने टाइम में इतना रिडक्शन हो रहा है, that is okay. So when this t1 tends to RC, then what will happen, then this V1 tends to 0. So that's why now I will put t1 is equal to RC and V1 is equals to 0 in this equation. So then why what I will get, V minus V1 divided by T1. What it becomes? It becomes V minus 0 divided by RC. Means it is V minus V1 divided by T1 is equal to V divided by RC. Is it? So this is what final thing. Reduction, reduction. I have explained, or whatever I am describing, I have described in the form of equation. Now just rearrange this. By rearranging this, V minus V1 divided by V is equals to T1 divided by RC. This is what the same equation I got. Look at this. This is what same equation I am getting. V minus V1 divided by V is equals to T1 divided by RC. Yes, that's what I am getting. So these two equations, so this one and this one, both are same. Is it? Either you go by this way, or if you understand by previous method, no problem. But you need to understand that V minus V1 divided by V, I am getting as T1 divided by RC. But see this next thing, that is V minus V1 divided by V. This thing is known to me. What is that? It is actually a sag. It is actually a sag. So I can clearly write sag is equals to T1 divided by RC. Now what is that RC? RC is a time constant of RC network which is equivalent to amplifier. Amplifier को हमने RC network में convert किया है. So T1 by RC is what my sag. But now what is the T1? But now let me elaborate about T1. So T1 is a, actually what is the T1? It is a half period. It is a half period. See, we have considered only positive cycle, is it? This is what positive cycle we have considered. We have not considered a negative cycle like this. ये तो हमने consider किया ही नहीं. We have considered only that much, and this we treated it as a T1. So if I say total time period of a complete cycle is T, if total cycle is T, then what will be the value of T1? T1 will be, it is T divided by 2. T1 will be T divided by 2. Then what will be the value of sag? Sag will be, it is T divided by 2 divided by RC. It means T divided by twice of RC. But what is T actually? Time period. If I want it in the form of frequency, then T is equals to 1 divided by F. This is well known. Put the value of T in above equation, then equation of sag. So I will again write sag is equals to, now put this value of T in this equation. It means it is 1 divided by 2 F. RC will be as it is. Sag is equals to 1 divided by 2F RC. Now if I rearrange this equation or divide and multiply the same with the pi in your language, then what I will get? See, I am multiplying with pi to the numerator. Then obviously I need to do this. See, pi will get cancelled and equation will remain same. Is it? Now see, let me rearrange this again. Now that is important. Now look at this pi divided by, see what I am doing. Look at here what I am doing. F divided by 1 divided by 2 pi RC. Now just check whether I'm having same equation. This equation is same as this. This f 2 pi rc, that's what it is, f 2 pi rc. Yes, it is same. But now why I'm doing this, why I'm rearranging this? Because I want this term, I want this term. What is this? It is 1 divided by 2 pi rc is a, okay, let me change the pen. It is a not lower as such, I will say it is a cutoff frequency. This is frequency for RC network. That network, in my case, that RC network, for me it is an amplifier. ये RC network क्या है? For us it is amplifier, क्योंकि amplifier को ही हमने RC network में convert किया है, is it not? So that RC network is nothing but my amplifier. But 1 divided by 2 pi RC is a cutoff frequency for RC network. So if I am saying that RC network is my amplifier, then this 1 divided by 2 pi RC will be my lower cutoff frequency, because now I am in the world of amplifier. Is it? So can I put this value here in our equation? Let me change the pen again, and then let me write what is sag then. Sag is equals to pi divided by f divided by 1 divided by 2 pi rc is nothing but lower cutoff frequency. Now what is that f? FL is lower cutoff frequency, that is okay. FL is lower cutoff frequency. Lower cutoff frequency. What is that f? F is actually signal frequency. In most English language, yes, the C of input signal that is applied. Applied input signal. Now all will get that. Signal frequency, it is the frequency of applied input signal, that is sag is equals to pi f divided by fl. Okay, let me simplify this further. Sag is equals to pi fl divided by f. Now look at this, the sag I have mentioned in the form of lower cutoff frequency as well as applied frequency. We know that applied frequency is very small because we are doing this at lower frequencies. Is it? At lower frequencies sag produced. So f is equals to sag is equals to pi fl divided by f. You can write the same equation, you can rearrange this to get lower cutoff frequency also. Now what is that lower cutoff frequency then? Okay, let me rearrange this. Lower cutoff frequency fl is equals to sag multiplied by frequency divided by pi. See, rearrange that is what my sag is. Now what do you mean by that? See, a sag is present in the output. It means there is a problem with the transmitter's lower cutoff frequency or the amplifier's lower cutoff frequency. Is it? And I said it's not a problem as such, it's a practical behavior of an amplifier. Is it? So means sag is it? It means when you will get the sag or when you will get the tilt, when you will get reduction in the output voltage, obviously at lower frequency. Is it? So at lower frequency you will get that, and this is the sag. No, generally at the time of exam there was some problems or numericals based on that sag, and even some people ask you to derive that equation of sag in terms of lower cutoff frequency and the applied signal frequency. Is it? So this is all about lower cutoff frequency and sag. What happens at lower frequency? Is it? So as we started with the square wave testing, and as somewhere I am going to use it, that's why I explained the sag. But now at higher frequencies, I said at higher frequencies what I am getting, at higher frequencies I will get this. Yes, this kind of waveforms I will get at higher frequencies. So at higher frequencies, if I am getting this, it means higher frequencies, or what thing that I can say is at higher frequencies amplifier will give output like this when we apply square wave. This is a square wave response of an amplifier at higher frequencies. Is it? Now what I want from that waveform, is it? मुझे क्या चाहिए इस waveform से? What I basically need, is it? What I want to tell you, I want to tell you about the rise time. Is it? Okay, to explain that rise time, okay, let me draw the signal, or let me draw the nice waveform. Okay, I feel this is nice. Yes, that is okay. If this is the middle line, हाँ ठीक तो लग रहा है, that is okay. हाँ, see, because drawing on the digital pen or with the digital pen is quite hectic actually. So this is what output at higher frequency, output at higher frequency. Now look at this, from that output voltage, what is my concern? My concern is if this is what my 10% level. Look at this, if I want to draw a line, okay, let me draw a straight line instead, that's always better. What happened? Come on, undo is not working. Forget undo, I'll use that eraser and I'll erase that. Yes, and now I'll draw a line here somewhere. That's quite okay. So this is what my output voltage on x and y axis. Is it? Now look at this. This is a 0th level. I'm talking about the amplitude, output voltage magnitude. This is a 10% level, where here it is a 50% level, 50% maximum output voltage, and somewhere here it is 100% level. Look at this, 100%. I'll say maximum is 100%, and then here somewhere it is 90% level. So this is 90%. This is simply of output voltage versus time. Output voltage versus time. Now, in that, there is a small concept of rise time. Is it? So, rise time is a very common concept, and you are well known about that. Is it? You have studied, you might have studied in MI, that is measurement and instrumentation. You might have studied the same thing in network analysis. Was it? So, thing is known, but still, I want to tell you that rise time is basically a period required for the output voltage to increase from its 10% level to the 90% level. Now, what is the 10% level? This is 10% level. What is 90% level? 90% level is this much. So, this time, उसको 10 से 90% increase होने के लिए जितना time लगता है, that time is called rise time. Is it? It is divided by TR. Let me write it as an rise time. Is it? And that rise time can be derived. That can be derived from the equation of a capacitor charging and discharging. That we are not going to derive the equation. I just want to tell you the concept of rise time. So that's why I'm telling you the concept. Now, if I want to express that rise time in the form of higher frequency, because I'm getting that kind of waveform at higher frequencies, then we can prove that rise time is 0.35 divided by higher frequency. Is it? So derivation is not part of our syllabus, but still, if you want derivation, anyone is interested into that derivation, this particularly, then please don't hesitate. I'll explain that derivation. I will give you an extra lecture on that derivation of rise time, because it needs a capacitor charging discharging equations that I need to tell you, and this is not part of this chapter actually, but still, if you are interested, Please let me know. I'll tell you that. Now, in terms of higher cutoff frequency, FH, just rearrange it. What is that FH then? 0.5 divided by rise time. That's what. Is it? That's what the small concept of rise time I wanted to tell you. I can write the definition of rise time. Right? But it is very common. It is well known to everyone. So what is the definition? It is the time required for the output voltage to increase from its 10% level to the 90% level. 10% से 90% तक जाने में कितना टाइम लगता है उसको? That time is what? Rise time. Is that? So those things basically are needed to understand higher frequency response. Is that? So that Miller theorem, that sag, rise time, or square wave testing, whatever we say, is the some prerequisite. Is that? ये knowledge आपको basically needed to understand the higher frequency response. So that's why we are covering this here separately. Is it? Now henceforth, on next part or next forthcoming thing is a higher frequency response. Is it? So prerequisite तो हमने खत्म कर लिया. Now we can start with higher frequency response. So let us start with what is that higher frequency response. Is that? So if I want to start with higher frequency response, I need to understand the BJT construction first. Is that? Okay, let me write it. High frequency response. Higher frequency response. Is it? So whenever I say higher frequency response, basically the first thing that come in mind is pi model. Pi model. As like this is what at lower frequency. Like this frequency, I have. Is it? Okay, I think we need to stop here. In next lecture, we will start this higher frequency model. All right. Thanks a lot.